Students, in the previous lessons we saw aromaticity, what is aromatic character, and how aromatic compounds undergo electrophilic substitution reactions, and also we saw important aromatic electrophilic substitutions like nitration, sulfonation, chlorination, Friedel-Crafts alkylation and Friedel-Crafts acylation. We also saw how electrophiles are generated in each case. Having seen that, we also saw the mechanism of aromatic electrophilic substitution reactions last class. Now, with the help of the mechanisms, we shall answer a few questions today. The first question: explain why Friedel-Crafts alkylation undergoes polysubstitution. My dear students, we saw Friedel-Crafts reactions have two types. One is alkylation reaction and acylation reaction. Now, I will write the aromatic hydrocarbon ARH. All along I was using benzene as an example or naphthalene as an example. Now, this is the general formula of ARH, meaning aromatic hydrocarbon. Now, this can react with alkyl halide in the presence of anhydrous AlCl3, to form hydrogen atom is being substituted by an alkyl group and you get H. So, this was the Friedel-Crafts alkylation reaction. Now, very quickly we will go through the mechanism also as a recap. Alkyl, let us take an alkyl chloride and I react with anhydrous, perfectly dry anhydrous AlCl3 to form R plus carbocation and AlCl4 minus. Now, this is the generation of the electrophile, and the next step ARH, aromatic hydrocarbon, attacked by the electrophile. The second step, I told you, my dear students, this is the rate determining step also, because this is the slowest step. The most difficult step in a reaction is called the rate determining step. It forms an arenium ion. I told you this is an intermediate. Ar, you have both the hydrogen and the alkyl group attached, and the entire thing should have a positive charge. This is called the arenium ion. And the last step, ArRH, this is the arenium ion, can lose a proton to form ArR, alkyl substituted aromatic compound, and of course H plus. Now, this is being done by, let us also pose a few questions before we go to the specific question. Namely, why should this be the rate determining step? I also told you this is an aromatic compound. All aromatic compounds have got unusual stability, aromaticity is lost. And once again, this is not an aromatic compound, the product is going to be aromatic compound, unusual stability, therefore this should be very spontaneous, very fast, and this is going to be the slowest step here. Maybe at one particular point of time I shall explain to you the significance of the slowest step, rate determining step also. Now, which reagent is going to do this process? Deprotonation, attack of the electrophile here, this is called the deprotonation, and which is going to remove the proton here? That could be one of the question. Which of the following, I will frame the question now, probably you can guess the answer here. Which of the following substances could remove the proton here? One could be alkyl halide, the other one is going to be AlCl3, the third one is going to be R plus, and the fourth one could be AlCl4 minus. Now, if you look into the answer here, AlCl4 minus, this is going to act as a Lewis base, and this is going to be an acid, and it is once again converted into AlCl3 and HCl. And so what are you going to do with this AlCl3? Again, it is going to behave as a catalyst. That is the reason why aluminum chloride behaves as a catalyst here. Aluminum chloride behaves as a catalyst. So, it generates a carbocation, again regenerated at the end of the reaction. So, if this is going to be the mechanism, my dear students, what type of carbocation can I use? Now, let us start with the simplest carbocation. Supposing I use methyl carbocation from methyl chloride, methyl carbocation from methyl chloride, CH3Cl, and ethyl carbocation, CH3, CH2 plus, and this can be generated from the ethyl C2H5Cl. Now, I can go ahead with N-propyl carbocation, N-propyl carbocation, and generated again from the N-propyl chloride here, and so on and so forth here. Now, if this is going to attack the benzene, we are going to get toluene. Look at this, C6H6 plus CH3 plus, so the product is going to be toluene here. Now, in this case also there is no problem, my dear student. Now, if this is going to be reacted with C2H5 plus, and you are going to get C6H5 C2 ethyl benzene. Yes. Students, before we see what are the different products when benzene is reacted with N-propyl chloride, we will go into the important aspect of this, explain why Friedel-Crafts alkylation reaction undergoes polysubstitution. Now, we take benzene. When this is going to be reacted with methyl chloride in the presence of anhydrous AlCl3, the product is going to be methyl benzene. We know methyl benzene is also known as toluene. Methyl benzene is known as toluene. This is a commercial name, and toluene is also accepted IUPAC name. Toluene. Toluene is also accepted IUPAC. Right. Now, when you are going to take benzene, 1 mole of benzene and excess of methyl chloride in the presence of catalyst, you get different products in the reaction vessel. One is going to be toluene, and this again is subjected to Friedel-Crafts reaction. You will be getting dimethyl benzene, and dimethyl benzene again is going to be attacked by methyl. You get trimethyl benzene, tetramethyl benzene, pentamethyl benzene, and hexamethyl benzene. And my dear students, it will be really, you will be surprised to know at the end of the reaction you will also have some unreacted benzene, and that is what is meant by polysubstitution reaction. Now, why should be the reason, what should be the reason for this? Now, benzene is attacked by methyl chloride, and let us say we have got 2 products here. This is going to be benzene and this is going to be toluene, and toluene, the methyl group, we know this is activating group. Methyl group is an activating group. It releases an electron into the benzene ring. So, when you compare the benzene and toluene has got higher electron density. Now, what is the electrophile here? CH3 plus. Electrophile always attacks a compound which has got higher electron density. Therefore, after some time, any methyl carbocation will not attack your benzene, will start attacking your toluene. So, what happened when toluene is going to be further subjected to methyl chloride here in the presence of anhydrous aluminum chloride? Now, the second product is going to be C6H4 CH3 twice. This is called dimethyl benzene. Dimethyl benzenes are known as xylenes. Xylenes or dimethyl benzenes. Now, let me ask you one question, my dear students here. How many disubstituted products are possible in the case of benzene? In the case of monosubstituted product, only one. Whether you have got the methyl group here or any one of the 6 carbon atoms, they are all called toluene or methyl benzene. Now, here you would know there are going to be 3 important compounds here. One is called orthoxylene, the other one is called metaxylene, and the third one is called paraxylene. You know what is orthoxylene? It is going to be 1,2 substituted benzene. 1,3-dimethyl benzene is called metaxylene, and 1,4-dimethyl benzenes are called this. For example, I can write those structures here. This is going to be, if you write a methyl group and the adjacent carbon atom, this is called ortho group. and if you write in the 1/3 position, we have got the methyl group and the methyl group, this is called this. Now, in the case of 1,4, this is 1,4, this is called ortho, this is called the meta and the para. Therefore, after some time what happened? Any incoming attacking electrophile will not go anywhere near methyl toluene or benzene, and this is going to be, there are two activating groups, electron releasing group. The electron density in this xylene will be much greater than toluene than this. So, any incoming electrophile will attack the xylene to form trimethyl benzene. Okay, well, let us proceed here. Now, if this is going to be attacked by all the three, attacked by methyl chloride in the presence of anhydrous aluminum chloride, I end up with C6H3 CH3 thrice. Now, this in turn is going to react with C6H2 CH4 4 times CH3 4 times tetramethyl benzene and etc. etc. Because every time the product becomes more activated because they have got higher electron density. Therefore, that is the reason why. So, at the end of it, I will give you a visualization for you. Let us take 100 molecules of benzene. You are going to react excess of methyl chloride or even 100 molecules, and some 80 molecules are attacked, converted into toluene. And at that stage, what happened? The toluene is 80% of the toluene is going to be converted into trimethyl benzene. 80% of trimethyl benzene is going to be converted into tetramethyl benzene, etc., etc. So, you will have some unreacted benzene also at the end of the reaction. So, what is the answer? One sentence answer. Explain why Friedel-Crafts alkylation reaction undergoes polysubstitution reaction. Every time product becomes more reactive than the starting material, toluene becomes more reactive than benzene, xylene becomes more reactive than benzene.